What up?
Not too much.
Hello?
Hey.
Are you guys ready? Or you waiting for me, or what's?
Basically waiting on you.
Let's just start then. Sorry.
Can everyone hear everyone?
Yeah.
Yep.
Alright. I suppose before we start getting into anything, Ron sent me a text today. PMPs, we are, as co-op, supposed to be doing them. So if you haven't done that, you need to get that to Elizabeth.
Okay. I already sent mine in.
Alright, I don't know if Elizabeth has co-ops in a different group or what, because apparently she didn't have mine, and I sent her mine on the day that it was due. But
maybe I should email her right now and make sure, 'cause she never gave me like a confirmation about that.
So let's see here. Also, before we really start getting into too much, I'd like to hear some comments about how we want to do class with adding Todd as far as filling out the wiki goes. I'm still kind of at a loss for what to do about that. I can't think of an extra topic to add.
Well, I would be more than happy to pick up or help in all three, or take a third of each topic. Or how many topics are there?
There's 3.
So
currently.
Something like that, unless someone has a better idea, or if you want me to do something other than the wiki page.
I don't know.
Beth.
I guess I can't think of any more sections to add or anything, so that might work.
So,
Kate, I can't hear you. You're really, really low. I don't know if there's a way that I can boost your volume.
You should turn on your camera. I just got a notice for it. I don't know what I did. What is this?
Me?
Oh, Kate.
Oh.
Oh, yeah. Here it comes. PMP, that's a good question. So, what parts of the wiki page? I guess I'm still catching up. I watched the first video and half of the second video.
Okay.
I've just been swamped at work and it's winded down. I'm actually at work right now, but
yeah.
I'll be able to catch up and do whatever I need to participate and get everything up to.
Alright, just to kind of tell you a little bit about what we're doing under the fundamental knowledge section. All the topics that we cover, there's 3 sections: an introduction and description, examples in the real world and why this topic is important subsection. And then from there, what I was having everyone else do was just every week you're going to be assigned one section to write a couple paragraphs about, 1 to 2 paragraphs, or about that much information. So
Okay.
the problem with kind of splitting up that work is then it becomes really hard to grade. That's my main concern. Oh, sorry, Kate. I can
Okay.
barely hear you.
Okay. Well, I could type it in the chat thing, but I don't know if anyone's reading that.
I can hear you.
Okay. Well, I have 2 ideas for sections that we could add to each. We could add like a further description, more in detail, because all we have is an introduction
Okay.
and then examples, and then basically like a conclusion. We could add a further detailed description, or we could do like definition, terms, something like that.
Okay. So do you have? I guess I'm having trouble. I'm looking at the page right now, and I don't see. Okay, introduction, description. The 2 main types of signals are followed as analog digital. So the examples in the real world, and then we have why this topic is important.
Yep.
And so you're proposing we add a section that would go maybe a conclusion section.
She was more going about
Short already.
kind of splitting up the introduction and description into kind of a more broad introduction and then a detailed, this is what this topic is really about.
Okay.
And you could put definitions in there, terms, stuff like that.
Yeah.
Otherwise, I just think our sections are really brief. So.
Okay.
Okay. So take out introduction / description and just leave it as introduction, and then make description its own piece.
Yep.
where I explain time series, for instance, or what an analog system is more specifically.
Yeah.
Digital signal.
And going kind of off what Kate was describing, just kind of using that as, this is what the definition of an analog signal is, this is what the definition of a discrete signal is. Here's really a working example of or not an example, but a working definition of what they are and how they apply. So that's a good thought, Kate, and I think that will probably be how we go about it. So Todd, I'm gonna put you in charge of doing this week's and next week's for that section.
This week's and next week's. Okay.
Yep, and then from there we'll go about continuing kind of the drop down and you do the next section.
Okay, when is the due date for this?
So next Wednesday, the topic number 2, so understanding of how signals can be represented mathematically. That's when that part of the wiki is due. And I don't know, do you think you can get that extra description done for the first topic also at that time?
It'll be tough. I'll do what I can, and I think that I can add to the catching up on that one, but I can definitely do the homework now.
Okay.
And then fill in the rest.
Yeah, I'll have you focus on the understanding of signals mathematically. Have that due next week, and whenever you get extra time to go back to last week's that was due today, go back and add that extra description. So
okay, understanding. So here I see understanding how signals could be represented mathematically. we obviously haven't done the lecture yet, so my confusion would be I would just want to know like
so-
which terms you want defined.
So, understanding of how signals can be represented mathematically was last week's topic, and then, or 2 weeks ago, right? No,
You were talking
Because
about the
system-
sign.
yeah. So last week we covered mathematical representations of signals. So what I would want you to do is kind of write down a description of, you know, that one's kind of tough. Maybe going into what is a unit function, what is a pulse function, what their mathematical symbols are, so things like that.
Okay. And that would be for next week?
Yep.
And okay.
And at the beginning of the class, so this week we're actually supposed to discuss at the beginning information that everyone has found for kind of their sections and areas that they can share. So I suppose that's kind of a good segue into, did anyone find any information that might be relevant to someone else's topic?
Sources. I was thinking about putting them up too. A lot of PDPs. Yeah, a lot of PDFs on the information. A lot of different colleges and stuff. There seems to be a ton of information on it out there.
Yep.
I was gonna put a couple links up.
Yeah, any information that, oh, Kate, you, oh wait, that was before. Okay, I'm sorry, I'm reading the, IMs. Okay, Todd, might be a good idea to mute your mic when you're not talking. Oh, Todd, are you getting a lot of feedback? Okay. Alright. So yeah, if you're not talking, might be a good idea to mute your mic. But going back to what Charlie was saying, yes, if you're finding information, I definitely encourage you to post where you found information, maybe just adding in kind of a general resources at the bottom. I can take on that responsibility. I can basically go on to each section and add on a resource and just post links to whatever information you found.
Yeah, I've found full chapters of books and stuff online. So, I don't know. That's why I was kind of gonna post it.
Okay. So I will actually do that right now, in fact. And I'll switch up the way that it's laid out too, so that it includes the description. So if anyone else has any more information to add, go ahead and speak up.
What are you doing right now, James? Creating a part in the wiki?
Yeah, I'm changing to include a description section and also add a resource section where you can just post your links.
Okay. Yep.
Do they call the unit function the unit step function? Is that the same thing?
There might be some areas that call it that. The unit function is more of just, it's kind of like a DC signal. It's a constant at one value. Whereas a step kind of jumps up and down. But what it could be, yeah.
So a unit step function that's just at a steady state would just have, I guess, one step, and that's, let's say,
Yep.
DC1, where a unit step function that's not being a steady state would then have steps, like a DC object.
Yep.
Okay. Okay. And then the impulse function, was that another one you wanted me to talk about?
Yeah, basically if any signals that you can find with any information that you can find on different functions, whether it be the unit function, whether it be the discrete delta function, sine waves, cosine waves, anything.
Okay, yeah, I found a delta function that I found some stuff right away on signals, so
Okay,
I'll look over that and I'll make something.
all right. Does anyone else have anything to add to information that you've been able to find?
As far as next week's topic.
Yeah, for your wiki,
I think the most interesting one for examples in the real world for me was like various filters and things, because you have to analyze the signal and then with whatever the Laplace transform and all that.
Yep.
Finding out how to build that filter.
Okay. Yeah, and that gets into a lot more detail. Laplace transforms and really there's a lot of different transforms out there that are used to manipulate signals in different ways to analyze them. Laplace being one of the more common ones. Obviously we aren't going to get that deep into it, but a lot of the computer equations and things like that are estimates of Laplace transforms and applying it to signals to kind of make the processing job easier. So it's a lot more electrical based, you know, get into it and you'll see a lot of that. Probably one of the few areas where you actually see an integral in engineering. So, I suppose since we're starting week 3, which is basically the halfway point for information that we're actually going to be covering, I suppose one question that I want to ask is, are you actually seeing a lot of this in your position? Because it's kind of going to come up to a head here as you start working on your DLAs, trying to find this information. So I suppose let's just kind of go person by person. Charlie, we can start with you. Are you seeing any of this information in your work?
Not so much yet, but I'm just about to start finite element analysis. And, we're gonna be talking about like vibrations and stuff, so I'm pretty sure that's gonna come up pretty soon.
Okay. Kate?
My mic is up. I don't know if you guys can hear me.
I can kind of hear you. You're in and out.
Can you hear me? Can I just type it on the chat?
Yeah, just go ahead and type it in the chat. Alright. Kate says this class is very relevant to what I do in my job. We analyze hundreds of signals and systems of our plant every day. We monitor the samples and trends of everything from mill vibration to nitrous oxide limitations and temperature spikes. So yeah, that's a really good couple of examples that are really important for what Kate's doing. So that's a really good area to have to start for DLA. Todd?
Well, I originally started thinking about like instruments for fire trucks and something, but one that I like the most that I think is practical is sort of in big industrial buildings or even apartment complexes, you have linked fire. Oh my gosh, they sound off when there's smoke alarms. And what it'll do is, so there's a couple different ways they go off. Some of them are temperature sensitive, and so that's a very analog thing, heat or smoke. And so what it does, it has to convert it and send it to a central processing system, which is usually if you go to an apartment complex, you see fire department only, and it'll tell you where or what, or if there's water flowing from a sprinkler head. And so all of those things are very physical, analog, and they are converted digitally, and sometimes even off-site to a 24-hour alarm system company, something like that.
Okay. Justin?
I think we lost him. I don't see him on here. Is he on here?
He just sent me a text. Can you add me to the call? It disconnected me. Alright. You there, Justin?
Yeah.
Alright, I'm not sure when you got dropped.
Right as Kate started to talk.
Okay. Basically, we've just been going around discussing areas and signals that apply to our jobs. So if there's any examples that you've seen in your job currently that kind of the stuff that we've been talking about applies.
I don't directly work with, I would say, any of this, but we do have a test facility within R&D that
Okay.
does work with different sensors and things of that nature. So I do have access to that if I need to.
It doesn't have to be, you're actually working in it. It's just understanding that, there's an area in your industry that actually has this applicable.
Yep.
So that's good. As far as me, I work in electronic sign boards, so I'm dealing with signals. Again, not directly like Justin mentioned. Very rarely am I ever working with any type of electronics, but working next to it, having the signals that are input into these displays is something that is good to know how to manipulate. I gave the example of knowing how to kind of mirror an image that's on one of these boards if something were to happen. That'd be something really helpful to know. Just for analyzing, what's going wrong. So yeah, that's a good. So I suppose now would be a good time to cover the homework that I sent out for this week. I'll pull it up here. Basically going over what is a system. And to answer that question, basically what a system comes down to is an input and an output. That's brought up in digital logic. Your system, your logic gates are basically consistent of just something coming in, some signal coming in, and putting out a different signal. Or even potentially the same signal. But that's what really defines systems, is a set of inputs and outputs. what do you think a linear system and a time invariant system is? The reason that I asked this question is not because I thought that you would find directly the answer, but specifically getting your head around these two terms, a linear system and a variant or time invariant system. I know for the class that I had with Muhammad that the first time that we saw a linear system, the first thing that came to our mind was y equals mx plus b. Just a straight line, and we thought that that was a linear system. But if you've done some research, I'm actually going to share my screen here, if I can remember how to do that. Share screens. So basically, a linear system is one that ultimately your inputs mimic your outputs. So you might have x1 of t going through a system, we'll call it h, and your output is y1 of t. And you get the same thing except it will be x2 and y2 if you put in a different signal. Where linear and nonlinear come in is what happens when you put in x1 plus x2 into the system. And there's a couple different things that can happen. You can either get y1 plus y2, which is a linear system, it makes sense, or you can get something that's completely different, which would be a nonlinear system. So it's going kind of against convention here. And there's one other test that goes along with this. I just need to remind myself on this quick. Oh, so it kind of comes down to the same thing. Basically, you're not going to see this as y1 plus y2 all the time, so you might have to simplify it. It might be simplified when you put it in, so you might see, rather than y1 plus y2 directly, it might be z, a different function. But if y1 plus y2 is equal to z, then you still have a linear system. So basically, if you're following this kind of logical order, you're a linear system. If you're not following this linear order, you're a nonlinear system. Time variant and time invariant are a lot easier to understand than this because it doesn't involve math at all. So let's say we have a graph, an exponential growth graph. Basically, this starts at 0 and ends at, well, it never really ends. If you were to put this through a system and you get the same graph but shifted, so let's say it starts at some number but it looks exactly the same, That's something called a time invariant system. And one way to think about this is kind of like capacitors charging. So a capacitor is going to charge the same way no matter when it gets its first charge. So if you apply voltage to it at point 0, it's going to charge this way. If you apply it at point 1, it's going to charge this way. If you apply it to point X, it's going to look exactly the same. A time variant would be something where this graph changes. So something that's time variant might be a got a message. Okay, Todd's down. Can anyone else hear me? Okay. Charlie, are you back on? Alright, something's going on. I think it might be my internet connection. Alright, Kate, if you can still hear me, I'm going to reset my internet and I will call everyone right back. I'll send out an email quick. Oh.
I can hear you now.
Okay. I don't know if that was my internet. Let me try adding people back in here. Back in business?
Yeah.
Alright. I have absolutely no idea where we got cut off at.
Last thing I heard is time invariant system capacitor.
Alright. Am I still sharing my screen with everyone?
I can't see it, James.
Alright,
I'm still.
on your phone. Alright. Well,
I'll rewatch the video.
okay.
Listen right now.
Well, really, I'm not showing too much. I suppose you might want to see what I'm talking about, so.
Essential function that's shifted.
Yep. So basically, if your graphs are looking the same, and you're shifting left and right, you know what, guys? I'm going to try and reset my router here quick, because I don't know if it's me, and I will be back in just a couple minutes.
Alright, I'm gonna go grab some food then.
Alright,
Just call me last or I'll join.
alright.
Goodbye.
Be right back, guys. Yeah, my modem is just in my living room, so. Really? Can you hear me, Charlie?
Yep.
Alright. Can you hear me, Justin?
Hey guys, the chief came, so I gotta jump off.
Okay.
I'll catch back up. Thanks for working with me, and I'll get started on that homework as soon as I can.
Yep.
Did you guys figure out the problem?
I still haven't connected to Justin. I don't know if I'm connected to Kate
Alright.
yet either.
Okay. Well, good luck. Text me or email me if you need me to do anything else, and just do what I gotta do, and I'm sure I can contact you if I get stuck or something.
Yep. Alright. Sounds good.
Thank you. Bye.
Bye. Alright, Kate, you couldn't see the shared screen either, correct? Back in, Justin?
What's that?
Are you back in?
Yep.
Alright. So apparently sharing the screen is kind of hard. I don't know. For the most part, I'm probably going to be done sharing the screen for right now anyways. So we kind of got cut off with discussing the what a time invariant system is, or a time variant system is, correct?
Yeah, basically what we were talking about with the cutting out.
Okay, so basically what a time variant or time invariant system is, time invariant if you have a specific graph and you start it at a different point in time. If you get the same exact response just shifted, then your system is time invariant. The time that it activates doesn't matter. The opposite of that would be time variant, where if your system responds differently at different times, then it's a time variant system. So those are the two main system properties that are really important in signals and systems. So you've got, different systems. You've got amplifiers, you've got feedback loops, things like that, that are just kind of a combination of a bunch of different systems. Overall, what's important for someone trying to analyze that information is if it's linear or nonlinear, variant or time invariant. And the reason for that is because a lot of the transforms and things like that actually require a very specific set of properties. One of them being an LTI system, which is a linear time invariant system. And actually, that's where one of the transforms that is very commonly used, that's absolutely the only way that the transform works. LTI systems, linear time invariant systems, are very, very rare, to the point where Muhammad made the analogy, if you were to pick up any random object in the universe, what's the chance of that being a banana? And that's the chance that a system, any system, is linear and time invariant. So let's just say that 1 in a million odds are good of being linear time invariant. Kate's having trouble, so she will just check the recording. That's fine. Kate, if you want to drop out of the call, spend this time doing something else, that'd be fine. Same goes for anyone else. Just send me a message on Skype before you drop out if things are going too poorly. So going back to that whole LTI systems are the ones that we can actually analyze. We can actually approximate most systems kind of in the same way that a derivative kind of estimates the curve of a graph. It's not one function that we're taking. We're taking it at a bunch of discrete points and then using that to kind of estimate. And straight lines, y equals mx, well, not y equals mx plus b, but those straight lines are linear time invariant systems in themselves. So by taking that derivative for the system, all of those points are linear time invariant, and then we can take it and use Laplace transforms, which are integrals, and go back and actually be able to analyze them differently. And that's where basically a lot of the calculations come into play. Again, we're not going to go deep into it, but the fact that most systems aren't linear time invariant and that we have to have these workarounds is kind of an important thing to understand about how we actually have to work with these signals. So, are there any questions up to this point? Okay. So going back into a system being just inputs and outputs, really anything can be a system, and everything that's physical is a system in one way or another, because we can analyze sound vibrations coming off of a material, heat absorption, and radiation. So everything is a system, if you want to get down to it. It's basically defining, is this my signal? What's my input? What is my output? Things like that. And it just goes back to the general engineering philosophy of we need to be able to define systems. What are our boundaries? Where do we want to draw them? Going to thermodynamics, is the entire power plant our system, or are we just looking at the loop? Are we closed? Are we open? To what degree are we closed and open? Things like that. So, systems, we've dealt with them a lot, so I won't go too far into it. So I suppose going more into the different types of systems that we see. I mentioned some of them before, amplifying circuits, or systems rather, where you're just taking an input and boosting the signal for it. There's feedback systems, which is your signal goes in, gets altered, and comes back in to the system. So one example would be your car's cruise control. So you've got a signal going in, whether it's the RPMs of your vehicle's engine, things like that, and then it's read in some way. The road alters it. The road and your car or the system. Your speed changes, goes through another small system to convert that into a different signal. Your car reads it, adjusts, and the loop continues. So that's feedback. Another one that's brought up is series or cascade. That's basically one system goes into the next, gets altered in different ways. That would go into kind of filtering. If you're looking for very specific areas, you can have certain systems that completely get rid of certain signals. So those are a couple examples. Let's see here. Delay systems, which is basically how we were talking about time variant or time invariant. Basically, is your system delaying the input some way. One would be, say, a switch. Your car is not running until you turn the ignition. It's going to react in hopefully the same way with time not being dependent. So hopefully your car is a time invariant system. We've got time reversal, which again gets kind of philosophical. Basically, you're trying to go back and have negative time, and it's weird. Frequency is a more common way to see that. Just because when you're dealing with frequencies, you can have those negative frequencies and they alter in different ways than a time or normal time system would. And those are really the main ones that I covered when I took the class. There are more systems. Any combination of systems can really ultimately be classified in any way that you want. You just have to define that system. That's pretty much what I wanted to cover. Systems are something that, again, we've covered time and time again, whether we really noticed it or not. A lot of the information that we learned in digital logic about how systems interact, the different logical gates interact, is pretty much the same logic that we're trying to get to with this. Your systems can be aligned in a different way. So I suppose the analogy is every logic gate is its own system. It alters a signal in a specific way. So I don't have too much else to discuss. Are there any questions that you two have?
I'm just trying to take it all
Yeah.
No comment.
So
So the plan is Todd will finish the description part.
yep, he will go into more depth than the introduction is. Let me just quick read the introduction here. Who's playing guitar?
Not me.
What?
I hear a guitar playing.
No, you don't.
Good to see you're utilizing your multitasking abilities there, Charlie.
What?
He doesn't have one.
I guess not.
I'm a college student. I multitask like a son of a bitch.
You're like a woman.
Hey now. I resent that comment.
You guys realize this is going on YouTube, right?
Really?
Yeah, that's where I've been posting all these videos, Charlie.
Oh. Yeah. No, I read all of this today.
Okay.
So that's why I can kind of strum along and listen at the same time.
So, the introduction is a pretty good way. I might want to see a little bit more information, just kind of digging a little bit deeper into, well, now that the description is going to be part of it. I'd say that this introduction is probably a good overall way of looking at it. That's kind of what I'm looking for. The description, of course, is going to be more factual. Might not be the best term for it, but it'll be a lot more term heavy, defining different terms and how they're utilized in the specific areas. So yeah, right now the plan is keep your assigned topic that I gave you last week. Todd will do the description for week 1 and week 2, and then we'll continue moving down and cycling through. So I forget what the assignments were. Charlie, I think next week you're doing the introduction, or this week for topic 2.
Yeah, that's right.
So next week you would, or for topic 3, you'd be doing description. Topic 4, you'd be doing examples.
Yeah, it just moves one down the line.
Yep. So that'll be the system that we continue with.
Yeah, that's good.
So I think that's about it. I will have some homework ready for you guys. Maybe some resources, I don't know. Resources have been kind of hard to come by on these topics just because finding them is kind of a pain, I know, and I don't want to take away from your searching and being able to find new information.
Yeah, I don't mind that aspect of it. I'm just gonna see what I can find. If you come across something that's more interesting, just looking at something that you give us,
Yep. Yeah, and basically it gives you a little bit more incentive to kind of read through it a little bit more deeply, rather than, okay, James thinks this is a good resource, so I better read this. Trying to find your specific information kind of helps that learning process, so I'd rather go that direction a little bit more. And honestly, what you find is probably going to be the same stuff that I find anyways.
Yeah.
Just because Google works that way. So, yeah, I don't have anything more. I'll get you the homework maybe tonight, maybe tomorrow. So, that should be it.
Sounds good.
Alright.
Thank you.
Don't forget to do PMPs. Or at least talk with... What's that, Charlie?
What do they do by?
They were due last Wednesday.
I emailed her and asked her for the details on it.
Okay. So yeah, probably email...
I'm gonna go to school on Friday, so I'll probably.
Okay. Yeah, if you have questions, probably just email Elizabeth and CC Ron if you have any questions that he might be able to answer. So, all right.
Alright. Thank you, James.
Yep.
Take it easy, boys.
You, Charlie.
All right. That's it. Good class.